Charge is distributed uniformly inside a solid sphere of radius r. The charge per unit volume inside the sphere is ρ. Find the electric field inside and outside of the sphere. Let's begin by drawing a sketch of this solid sphere. We have a sphere that is full of charge. This sphere has a radius of r. It has a uniform charge density of ρ, and that means that charge is uniformly distributed throughout the volume of the sphere. Our goal is to find the electric field both inside the sphere and outside the sphere. To do this, we should recognize one thing. Uniform spheres of charge has spherical symmetry. What that means is no matter how you rotate the sphere, no matter which hemisphere you look at, the charge distribution will look the same from any of those vantage points. And as we've learned previously, for a sphere that has a uniform distribution of charge, the electric field is going to match the symmetry of the geometry of the charge. And this symmetry is spherical symmetry. This means we have a good idea of what the electric field looks like. The electric field is going to point radially away from the center of this sphere of charge. Now, here's the thing though. The way I drew this picture, it seems that the electric field would be varying in a consistent way from inside the sphere and then to outside the sphere. Just remember that this sketch is just our rough sketch to remind ourselves that this sphere of uniform charge has spherical symmetry. The electric field, the way it varies, may vary completely differently once we are outside the sphere. We're going to first start with trying to find the electric field at an arbitrary point inside the sphere. So let's find the electric field somewhere between the center of the sphere and the surface of the sphere. Because the sphere of charge has spherical symmetry, Gauss's law is going to be the tool that I use to help me determine the electric field. Remember, Gauss's law says that the total flux of a closed surface is equal to the amount of charge contained within the volume enclosed by that surface divided by epsilon naught. Gauss's law is very powerful because it tells us that regardless of the shape or the size of a closed volume in space, the flux is always going to be based off of the amount of charge inside. Gauss's law becomes especially useful if our problem has some level of symmetry. And this level of symmetry will allow us to simplify the integral dramatically, as you'll see when we work this example. So to use Gauss's law, we have to come up with an enclosed surface. Or let me say a closed surface. This closed surface is going to have to contain a certain amount of charge. So let's add that closed surface to our diagram. If we want to find the electric field at an arbitrary point within the sphere, we'll say this point right here. This point has a distance of lowercase r from the center of the sphere. Let's create a Gaussian surface that is also a sphere centered at the center of the ball of charge. So this Gaussian surface, remember, is just a mathematical surface in space. It doesn't have to be a real physical surface. It just needs to be described mathematically. So this Gaussian sphere encloses a certain amount of charge. And according to Gauss's law, there's a relationship between the amount of charge, the electric field, and the Gaussian surface that is enclosing that electric field. So instead of looking at the entire ball of charge, let's look at the amount of charge that we are enclosing. This is just some fraction of the overall charge that we're enclosing. And because this ball of charge is spherically symmetric still, we know that the electric field outside of this ball of charge is going to share that symmetry. So these electric field lines are being drawn as if they're emanating from the center of this sphere of uniform charge. So here's our Gaussian surface. And the amount of charge we are enclosing in this Gaussian surface, I'll label it as Q enclosed. So let's look at the pieces of Gauss's law. So we have the electric field, and this is going to be the electric field on the surface. The surface has a total area of A. So this is the area differential at a spherical rectangle on the surface. And again, this is on the Gaussian surface. Here is the amount of charge that is inside our surface. And I want to emphasize the word inside or enclosed by the surface. So let's look at this. So let's look at the electric field. We have the electric field on the surface. So let's pick any of our points on our sphere. I'll just go ahead and pick this top point right here. This top electric field line has a certain magnitude and it has a certain direction. Because the electric field matches the symmetry of our charge, it is going to be parallel to the area differential at that point on our sphere. Now that area differential is from a representative spherical rectangle on the sphere. So it is the tiny, tiny bit of area in a small portion of our sphere. And at that location, the electric field is perpendicular to the sphere, and our area differential is also perpendicular to the sphere. So those two, the angle between those two is 0 degrees. Let's also look at the amount of charge enclosed by our Gaussian surface. Now we're not given the charge, but we are given the charge density. The charge density is rho. Now remember, charge per unit volume is defined to be this. dq dv, charge per unit volume. Because this is a uniform charge density, that means the amount of charge enclosed by that sphere divided by the volume of that Gaussian sphere will give us the density of our charge distribution. So now we have all the pieces in play. Let's go ahead and write Gauss's law for what we have. Gauss's law says that the total electric flux through a closed surface is equal to the charge enclosed by that surface divided by epsilon naught. This means that if we look at our surface and use one version of the dot product that says the magnitude of the electric field times the cosine of the angle between the electric field and the surface differential times the magnitude of the surface differential is equal to how much charge that we have enclosed divided by epsilon naught. Well, let's go ahead and come up with an expression for each of our pieces here. Since the electric field is constant at every point on the surface of this Gaussian sphere, it is then constant with respect to the area differential. So I could pull that outside of the integral. So then we have the integral of the area differential of the sphere, and that is equal to the amount of charge enclosed over epsilon naught. Well, from this relationship between the density of the charge distribution and charge enclosed, we could say that the amount of charge enclosed is equal to 4 pi r cubed rho. Let's use that expression. We have the integral, or we have the electric field. This integral of the surface differential ends up being equal to the area of the sphere. So let's write that, the area of the Gaussian sphere. And this is equal to Q enclosed, which we said is 4 pi r cubed rho, and this is divided by epsilon naught. Well, the area of the sphere is just 4 pi r squared for our Gaussian sphere, and this is equal to 4 pi r cubed rho. Ooh, I made a mistake. The volume of a sphere is 4/3 pi r cubed. So let me put a 4/3 down here, and this is a 4/3 right there, and this is a 4/3 right here, and this is a 4/3. Glad I caught that. We would have been off by a factor of 3. Okay, so we are now ready to evaluate the electric field once we do some simplifications. We have a 4 pi on the left that cancels with a 4 pi on the right. We have an r squared on the left that cancels with an r squared on the right. This means that the electric field, oh, and there's an epsilon naught over here at the bottom. So this means that the electric field is equal to 1/3 rho r over epsilon naught. Let's do a unit check to make sure we did everything right. Or at least if our units work out, then we know we probably didn't make a major mistake. So let's do a quick unit check. So we're going to compare the units on the left side of the equal sign to the right side. The unit of the electric field is a Newton per Coulomb. Constants don't have units. Charge density rho, well, that is a charge per unit volume, so Coulomb per meter cubed. Then we have the R that has units of meters. And then we have the epsilon naught. Epsilon naught has units of Coulomb squared per Newton meter squared. Well, let's see what we have here. Have this meter on top, cancels, and then these two will cancel with this meter. This Coulomb here cancels with the Coulomb on the bottom. When we evaluate these units, do some flipping and multiplying, we get a Newton per Coulomb. The units check. So that means that we could write the electric field as E as a function of R equals 1/3 rho R over epsilon naught R hat, where R hat is a unit vector pointing radially away from the center of the sphere, and R is the distance from the center of the sphere, and this will take us from 0 to the surface of the sphere. Notice with this electric field, it varies linearly as a function of distance. So if we were to plot this electric field as a function of distance, here is R, here's the magnitude of the electric field, here is the surface, here is the surface. That electric field would be 0 at the center of the sphere and increase linearly until we get to the surface of the sphere. And that makes sense because as you enclose more and more charge, the electric field should be getting larger. Now let's figure out the electric field outside the ball of charge. So just redrawing our charge, we have a uniform charge distribution. And we are interested in the electric field that is outside of this uniform sphere of charge. Since it's a uniform sphere of charge, we know the electric field is going to match the symmetry of the charge, which is spherical. The charge has radius r. Let's pick a point outside of the sphere, and we'll just say our point is right here, for example. And this distance, I will just call this distance a distance of lowercase r. Let's create a Gaussian surface that has that radius lowercase r. Here is our Gaussian sphere. Notice that at every point on this Gaussian sphere, the electric field is perpendicular to the plane of the sphere at that point. This is good for us because, once again, we can use Gauss's law to simplify our calculation of electric flux, which relates the electric field, the Gaussian surface, and the amount of charge inside. So let's use Gauss's law. So let's pick a point on the sphere. I'll pick this point where we have an area differential. And that area differential is perpendicular to our surface. This should look familiar. We have that the total flux through an enclosed surface is equal to the amount of charge inside that enclosed surface over epsilon naught. Because the electric field is uniform on the surface, and what I mean by uniform is it looks the same no matter where you are on the surface. It has the same magnitude and it has the same orientation relative to the surface. Because of that, Gauss's law is going to make the calculation of this integral go rather quickly. So let's look at this rho v. That is the representative of the amount of charge that we have enclosed. Now, the amount of charge we have enclosed is equal to the product of the uniform charge density times the volume that the actual charge encompasses. Because this was defined based off of charge, or based off of charge density, is charge per unit volume. If that charge distribution is uniform, then it is charge per volume in which the charge occupies. So this volume of the charge ends up being 4/3 pi capital R cubed, because it's only the volume that the charge occupies that tells us the amount of charge that's enclosed. Which means that our electric flux becomes the electric field, which we can pull outside of the integral because it's constant with respect to our area differential, times the integral over the Gaussian surface. Now again, we have to distinguish. This is our Gaussian surface here, is equal to the product of rho v over epsilon naught. And actually, let's go ahead and replace our volume now. Our volume is 4/3 pi capital R cubed. Well, the closed integral over our surface is just the area of our Gaussian surface. And this is equal to 4/3 rho pi over epsilon naught R cubed. The area of our Gaussian surface is 4 pi little r squared, because that's the radius of our Gaussian surface, is equal to 4/3 pi rho r cubed over epsilon naught. Well, the 4 pi cancels with a 4 pi. So this now becomes the electric field as a function of r is equal to 1/3 rho r cubed over epsilon naught times 1 over r squared, r hat for our unit vector. Now, if you look at this, notice this is saying that the magnitude of the electric field is inversely proportional to the distance squared from our charge. And that makes sense because this is an electric field due to a sphere of charge in which we are outside of the charge. And the farther and farther and farther away we go, that sphere of charge should look more and more like a point charge. And we know that electric fields due to point charges are inversely proportional to the distance squared from the center of that point charge. So it makes sense that our electric field would follow this inverse square law when we're outside of the sphere. Let's look at what this looks like for when we were inside the sphere. When we were inside the sphere, we had the electric field that varied linearly. That's a linear relationship with R. Here, so we could say that the electric field, when we are inside the sphere, is directly proportional to distance from the center of the sphere. While when we are outside the sphere, the electric field is inversely proportional to the distance squared. Now, that makes sense because, again, when you look at that sphere of charge, when we are inside the sphere, as we increase our distance from the center of the sphere, we are enclosing more and more charge. So as we enclose more and more charge when we're inside the sphere, we would expect that the electric field due to that charge inside will get stronger and stronger and stronger. And in this case, mathematically, it varies directly with distance. So if we were to sketch that, where the horizontal axis is a distance from the center of the charge, vertical axis is the magnitude of the electric field, this is indicating the point on the surface of the sphere, we would expect that the graph would look linear, or the electric field at the center of the sphere is 0, and we are increasing linearly to a maximum value. So this is the region for 0 less than or equal to r, less than or equal to capital R. And then when we are outside of that, we get the inverse square law. And that makes sense because now once we are outside that uniform sphere of charge, as you can see from our electric field lines, the electric field is weakening with distance.